Once again, welcome to our YouTube channel, Deep Learning Underground. Now, you might be thinking, what's a channel called Deep Learning Underground delving into, well, ancient Earth history?
A fair question.
It is. Well, while our name reflects our passion for uncovering deep foundational knowledge, getting to the bottom of things, today we're taking that ethos on a truly astounding journey back in time. Not into algorithms this time, but into Earth's most profound geological and biological shifts.
Hmm.
We're exploring a period that sounds, well, almost like science fiction, doesn't it? A time when it rained, not for days or weeks or even decades, but for 2 million years.
2 million. It's staggering.
Yes, you heard that right. 2 million years of continuous, pretty relentless downpour. And incredibly, this seemingly impossible event, it profoundly reshaped life on Earth. Specifically, it set the perfect stage for the age of dinosaurs to truly begin.
It really did.
We've been poring over the transcripts from a very well-regarded science channel, delving into the core research, and honestly, the insights are just incredible.
Indeed. Our mission today is to really unpack the geological and biological implications of this extraordinary period. We want to connect the intricate dots, between climate, geology, and evolution in a way that gives you, our listener, a truly comprehensive understanding.
Yeah, get the full picture.
Exactly. Prepare yourselves for some profound aha moments, because we're going to highlight how seemingly small, almost overlooked detail, things you might never consider, like the very specific digestive systems of ancient animals, played an absolutely massive, pivotal role
Right.
in shaping Earth's dominant life forms for millions of years to come.
Sounds fascinating.
It's a testament to the intricate, often surprising dance of planetary systems and life itself.
Yeah.
We're essentially fast-tracking you to becoming well-informed about one of Earth's most significant, yet perhaps lesser-known transitions.
Okay, let's unpack this then. Because to truly grasp the monumental significance of 2 million years of rain, we first need to understand what the world was like before this deluge.
Absolutely. Context is key.
Imagine Earth around 250 million years ago. This is the very start of the Triassic Period. Now, this wasn't some, green paradise. Quite the opposite, actually.
Far from it.
This was a world still desperately struggling, quite literally gasping for breath to recover from the Permian extinction.
The Great Dying.
Exactly, the Great Dying. For context, this was the single greatest mass extinction event in Earth's history. It wiped out something like, 96% of all marine species?
And about 70% of terrestrial vertebrate species. It was absolutely devastating.
This apocalyptic event. And the Earth that emerged from it was scarred, hot, and profoundly dry. The dominant characteristic of this, post-apocalyptic landscape was extreme heat and profound aridity. Think about it. The ocean wasn't just warm, it was apparently like a hot tub.
Uncomfortably warm, yeah.
And the air, it was thick with carbon dioxide, a potent greenhouse gas just relentlessly pumped into the atmosphere by colossal volcanic eruptions.
Yeah. Huge eruptions.
We're talking about a planet that was, by our standards, practically oven-baked and parched. The very atmosphere was holding on to heat, creating this global hothouse effect that would have been utterly alien to anything we experience today.
And a major player in creating this arid, almost alien environment was the configuration of Earth's land masses, the supercontinent of Pangea.
Right. Everything's smushed together.
Pretty much. Picture it. All of Earth's continental crust locked together from pole to pole, forming one colossal, unbroken landmass. Now, this wasn't just a geographical curiosity. It had profound climatic consequences.
That's who?
Well, with no major ocean breaks to interrupt the flow, rain clouds, which typically form over oceans, simply couldn't move much past the coastlines.
Oh, okay.
They dumped their moisture relatively quickly over the coastal fringes, leaving the vast interior of the continent utterly starved of water. Imagine air currents moving over thousands of kilometers of dry land, picking up basically no moisture and bringing no rain inland.
So a massive dry heartland.
Precisely. And to make matters worse, there were no big mountain ranges, no nascent Himalayas, no Rockies, no towering Andes to break up the low flat land. Nothing to force moist air upwards to cool and condense into rain.
The rain shadow effect, but on a giant scale.
On a continental scale, exactly. So what you had was this enormous, low-lying, relatively flat, and fundamentally arid continent stretching across the globe, where the hydrological cycle just couldn't penetrate the interior effectively.
And we can see this in the rocks.
Oh, absolutely. The evidence for this incredibly dry world is literally etched in the rocks beneath our feet, which is fascinating in itself. Rocks from that early Triassic period are predominantly swaths of red sandstones and soil deposit from dry woodlands.
Red rocks, like you see in deserts today.
Exactly.
Mm.
You won't find the extensive, lush coal swamps that had defined much of the preceding Permian period. The very color of the rock, that deep red, tells you a story of iron oxidation in dry, open air conditions, almost like desert rust.
Wow.
It's a stark geological record of a truly desiccated planet, painted in stone.
So we have this vast, parched, heat-baked landscape emerging from the Permian extinction, a world that seems almost inhospitable by modern standards. But life, as they say.
Finds a way. Always does.
It's important to remember that dinosaurs did exist in this dry, post-Permian world, but they weren't the dominant rulers we imagine from, say, the Jurassic or Cretaceous periods.
Not at all. Minor players, really.
They were still relatively minor players, really just vying for their place among other far more prevalent early reptiles and the strange reptile-like mammal ancestors that thrived in this environment. The stage was set, but the main act hadn't yet taken center stage.
Indeed. If you were to somehow, wander through this parched, hot landscape, you'd encounter some truly bizarre and fascinating creatures, all perfectly adapted to the dryness and the limited resources.
Like what?
Well, the dominant carnivores weren't huge dinosaurs, but a broad and diverse group of croc-like animals known as crurotarsans.
Croc-like, okay.
Yeah, this umbrella group included various reptiles like pseudosuchians and phytosaurs, which, whilst resembling modern crocodiles in some ways, occupied a far wider range of ecological niches than their modern counterparts. Take Ornithosuchus, for instance. This was a crudotarsan that possessed remarkably long hind legs.
Long legs?
Yeah, and could actually stand up and run on them when it needed to, perhaps to chase prey or escape danger.
Crikey, a running croc thing.
I can only imagine how awesome and terrifying that would have been to witness firsthand a large croc-like creature suddenly rearing up and sprinting on two legs across the dry plains.
Yeah, that certainly challenges our preconceptions of what a crocodile looks like.
Doesn't it just?
That's a truly vivid image. It certainly paints such a different picture of these ancient landscapes. But you mentioned other creatures, even stranger ones.
Oh yes, even stranger than those speedy croc analogs were the rhynchosaurs.
Rhynchosaurs, okay.
Yeah. These were the primary herbivores of the time, and they were quite distinctive. They possessed what paleontologists describe as parrot-like beaks, perfectly suited for clipping tough, low-lying vegetation.
Parrot beaks on a reptile body.
Pretty much. And some species even had these incredible prominent cheekbones, or more accurately, robust bony flanges, that would have provided powerful attachment points for their jaw muscles, allowing them to exert immense force when chewing their plant-based diet.
Built for tough stuff, then.
Absolutely. All of this was mounted on what's been humorously but accurately described as a rather sturdy, lizard-like body. Their specific adaptations tell us a great deal about the flora available in this dry environment, likely tough, low-growing plants that needed considerable processing.
Right, makes sense.
And then you had the Dicynodonts.
Dicynodonts.
These were arguably the most intriguing of the bunch for us because they were the closest things to true mammals at the time.
Really? Closer to us?
Surprisingly, yes. Despite being scaly, four-legged creatures, often with bills and tusks, a truly unique combination, they were actually more closely related to us, to mammals, than to the more reptilian Dimetrodon.
Ah, the one with the sailback.
That's the one. Dimetrodon is often mistakenly grouped with these true mammal ancestors due to its general reptilian appearance. But that distinction is crucial. Dimetrodon was a pelycosaur, a far more primitive synapsid, while Dicynodonts represented a later, more diverse branch on the evolutionary tree leading towards mammals.
Huh.
It's a fascinating reminder of the strange, diverse evolutionary paths life takes before settling on today's familiar forms.
That's a great point about the evolutionary lineage, highlighting how complex and nonlinear these paths can be. And these fascinating creatures, the crurotarsans, the rhynchosaurs, and especially the Dicynodonts, they were incredibly widespread for most of the early to mid-Triassic period, weren't they?
Absolutely dominated the terrestrial ecosystems.
In fact, one particular genus of Dicynodont known as Lystrosaurus, that one's quite famous, isn't it?
It is. It was so common, so widely distributed, and its fossils were found in so many far-flung parts of the world, Antarctica, India, Africa, North America,
Everywhere.
that its consistent global distribution actually played a crucial, undeniable role in helping scientists construct and confirm the theory of plate tectonics.
No way. This one creature helped prove continents moved.
Imagine that the fossil remains of a single, rather unusual creature helped us understand the fundamental movements of Earth's continents over geological time.
That's incredible.
It truly was a global indicator of the dominant life forms in that period, thriving across what was then Pangea. But despite their widespread success and their perfect adaptations to this hot, dry climate, these animals were, well, unknowingly, in for an absolutely massive shakeup.
Here it comes.
A climatic event was on the horizon that would fundamentally change the rules of the game and pave the way for a completely different set of rulers.
Here's where it gets really interesting, because that's precisely what happened. Starting around 234 million years ago, this hot, dry, rather stable climate suddenly, dramatically shifted.
The taps turned on.
They really did. The rains finally came to this parched world, and then they stayed. Not for a few minutes or a few years, but for 2 entire million years.
Just relentless.
This astonishing period of intense, prolonged rainfall is known as the Carnian Pluvial episode, or CPD. And when geologists first started finding the deposits left by these ancient floods, they were genuinely perplexed.
Understandably so.
These rocks just didn't seem to fit the established picture of a predominantly hot, dry, Triassic world that they thought they knew. It was a genuine scientific puzzle, a real anomaly in the geological record.
It truly was a puzzle, and the story of its discovery and verification is a testament to persistent scientific inquiry and the collaborative nature of global geology. In the early 1990s, two British geologists, Alistair Ruffell and Mike Sims, were working independently in areas where they expected to find the typical red, slowly deposited sands indicative of that dry Triassic climate.
Usual red stuff.
Exactly. But instead, what they unearthed in places like the Penarth Group in the UK were thick layers of river rocks, sediments from giant lakes, and clear evidence of coal swamps.
Coal swamps in the dry Triassic.
Precisely. These weren't subtle clues. These were all undeniable, unequivocal signs of massive, prolonged rainfall and widespread water bodies, lasting over the course of some 2 million years. This was a dramatic departure from the arid conditions inferred from the surrounding geological record.
But surely people thought it must be local, right? Just weird local floods.
That was the initial reaction, yes. What was even stranger, and initially led to significant skepticism among other geologists, was that these traces of a suddenly wet climate weren't just localized anomalies. As more and more data emerged, it became clear these signals were appearing everywhere, from England to the Americas to Israel, in regions that were geographically very far apart, even back then, on the supercontinent Pangea.
So it wasn't just one place.
Exactly. This was critical, as isolated floods could occur, but a global signature of prolonged wetness was something else entirely. For a while, the prevailing thought was, couldn't these anomalies just be explained by a lot of big, isolated local floods, perhaps in different regions at different times?
That's a reasonable initial hypothesis, isn't it? But then the evidence just kept coming in, consolidating into something far more profound.
Precisely. Over the next 2 decades, the evidence continued to mount, making that isolated local flood hypothesis increasingly untenable. More and more reports of these weird rocks kept trickling in from around the globe, all consistently pointing to a world that was undeniably getting wetter and wetter during the specific time window.
What kind of evidence?
The rocks revealed extensive coal deposits in Austria, clear traces of ancient lakes in Italy, distinct wet soils in Utah in North America, and unmistakable signs of giant rivers in China.
All over the world, then.
All over. And critically, they all consistently dated to the same relatively narrow window of time, between 232 and 234 million years ago, firmly placing it within the Carnian substage of the Triassic period. This overwhelming, globally distributed evidence eventually solidified the understanding of this phenomenon, which came to be definitively known as the Carnian Pluvial episode. It was a true paradigm shift in our understanding of Triassic climate.
And it's a brilliant name, isn't it? Carnian refers to the specific geologic age within the Triassic period when all of this incredible change happened. And pluvial just means rain. And let me tell you, the data suggests it rained a whole awful lot.
An understatement, perhaps.
Possibly. To give you a sense of the sheer scale of this downpour, one estimate, based on geological proxies, suggests that in what is now Utah, the average annual rainfall almost quadrupled during this period.
Quadrupled.
Yeah. It reached a staggering peak of 1,400 millimeters, or about 55 inches of rain a year. Now, For context, that's comparable to the annual rainfall you'd expect in a modern temperate rainforest today, like, say, in the Pacific Northwest of North America.
Or parts of the UK, even.
Exactly, or parts of the UK's Lake District. Imagine that. A region that was once a parched desert suddenly experiencing rainforest-level precipitation. The landscape would have been utterly transformed.
And it's crucial to understand that this wasn't just one giant biblical flood that came and went.
Right, not a single event.
No. This was more like floods every year all over the place for 2 million years. Imagine the relentless nature of that. The constant saturation of the landscape, the rivers perpetually swollen, new lakes forming, vast wetlands expanding. It wasn't an isolated transient event. It was a sustained global climatic transformation that fundamentally reshaped the Earth's surface and its ecosystems.
It truly was a wet intermezzo, as you called it earlier. I like that.
It is a delightful term, isn't it? Beautifully captures the spirit of this fascinating wet period within the generally arid Triassic. And with all this extraordinary unending rain, things were absolutely bound to change. And change they did in profound and unexpected ways.
And the biggest change.
One of the biggest, most significant changes was the sudden dramatic abundance of dinosaurs.
That's a striking way to put it, the wet intermezzo. It certainly captures the fleeting but transformative nature of this period. So what was the profound impact of the Carnian Pluvial episode on life? You mentioned that sudden and overwhelming abundance of dinosaurs.
That's right. If you look at the fossil record, at the very start of the CPE, dinosaurs accounted for approximately 5% of the fossils of terrestrial vertebrates unearthed across the globe.
Tiny fraction.
A mere fraction, right. But by the end of this 2 million-year wet period, that number had skyrocketed. Dinosaurs made up more than 90% of those same types of fossils.
90% from 5.
It's not just an increase, that's a complete flip in dominance, a true evolutionary shakeup that reordered the entire terrestrial ecosystem.
So this raises that fundamental question scientists have grappled with. What made the dinosaurs so suddenly successful? Were they inherently better adapted to this newly wet world, maybe with some unique physiological advantage that allowed them to outcompete their rivals directly? Or did other animals simply die off, making way for dinosaurs to effectively rule the world by default, simply because their competitors were no longer around to challenge them?
That's the absolute core of the mystery, isn't it? The immediate thought might be that the rain itself made them stronger or faster. But the real game changer wasn't necessarily the rain directly.
No.
Rather, it was what the rain brought with it. A veritable proliferation of giant plants.
Ah, the food source.
Exactly. Think about it. With that much moisture, the landscape would have transformed from those dry woodlands to lush, incredibly dense wet forests and expansive wetlands. During this exact time, the fossil record shows us a sudden and widespread abundance of large conifers, the ancestors of our modern pine trees,
Okay.
and also other substantial coal-forming plants, like the rather primordial-looking Bennettitales.
And at what now?
Bennettitales. These were ancient cone-bearing plants that resembled modern cycads, with stout trunks and fun-like leaves. And crucially, they formed significant coal deposits, indicating vast, dense, lush vegetation.
So big, tough plants.
These were robust, woody plants, vastly different from the sparse, low-lying flora of the arid Triassic. Now, for herbivores, the creatures that eat plants, this wasn't just a minor dietary tweak. This change in food supply, from sparse, low-lying, dry-adapted plants to towering, fibrous, woody trees, would have been an absolutely critical shift. It completely redefined what was available to eat, and crucially, what digestive systems were needed to process it.
That's a crucial distinction. It's not just more food, it's different food. So how did this new vegetation impact the previously dominant groups like the Rainforests and Dicynodonts? Did they adapt, or did they simply falter?
They largely faltered tragically. Consider the Rainforests, for example. We mentioned they were abundant, but they were also, quite simply, short.
Right. Couldn't reach high up.
And crucially, unlike some later dinosaurs, they couldn't stand on their hind legs to reach higher leaves. In a dry environment, where plants tended to stay closer to the ground and were perhaps less fibrous, this was perfectly fine. They were well adapted to graze what was available. But in a newly wet, dense forest dominated by tall, woody conifers, Rainforests would have been severely limited.
Stuck with the low stuff.
Exactly.
Yeah.
Only being able to eat smaller undergrowth plants or whatever leaves and fruit happened to fall to the ground. Their preferred accessible food sources would have become severely restricted, even as the overall plant biomass exploded.
What about the Dicynodonts, the ones closer to us?
Well, they're also primary herbivores at the time, but they faced an even more fundamental anatomical problem with the new plant life.
Yeah.
They didn't possess teeth specifically adapted for chewing fibrous material.
No grinding teeth.
Their characteristic bills and tusks were excellent for shearing or digging, but not for grinding tough wood. And, just as critically, they also didn't utilize gastroliths.
Gastroliths. Stomach stones.
That's right. Those small, smooth rocks that some animals, like many birds and modern crocodiles today, swallow in keeping their gizzards to help grind up tough plant material, acts as a kind of internal mill.
Okay.
Without either proper teeth for mastication or gastroliths for internal processing, Dicynodonts would have had an incredibly hard time breaking down and extracting nutrients from anything fibrous, like wood.
And we know this how? From fossils.
We have fascinating direct evidence. Fossilized Dicynodont poop, known as coprolites.
Ancient poo.
Exactly. Coprolites from this period have been found, and they consistently contain the digested remains of mostly soft ferns with only very small amounts of wood.
Wow, so clear evidence.
It clearly indicates their dietary limitations in the face of the new, tougher vegetation. It's an incredibly clear signal from the fossil record about their struggles.
That's an astonishing level of detail to extract from ancient fossilized droppings, and this is precisely where the dinosaur advantage becomes crystal clear, isn't it?
Absolutely.
Because in stark contrast to the Dicynodonts and Rhynchosaurs, the plant-eating dinosaurs that were around at the time, even the early ones, had both teeth, and they used gastroliths.
They had the toolkit?
They were perfectly equipped for this new, tougher diet. In fact, their own fossilized poop from this period tells a very different story.
The much woodier story.
Much woodier. Some dinosaur coprolites from this period show that their diet consisted of up to 85% wood.
85%? That's incredible.
That is an astonishing amount of fiber, and it speaks volumes about their superior efficiency in processing this new, abundant, but difficult to digest plant life. It's a remarkable example of natural selection at work, favoring those with the right tools for the new environment.
Couldn't put it better myself.
So if we connect all the dots here, the picture becomes incredibly clear. As the climate became wetter and wetter during the Carnian Pluvial episode, those soft, small ferns and low-lying plants that the Dicynodonts and Rhynchosaurs thrived on were rapidly replaced by these tall, woody conifers and other fibrous plants.
The landscape changed, the menu changed.
And because the Dicynodonts lacked the anatomical tools to process this tough, fibrous wood, and the Rhynchosaurs simply couldn't reach it, their primary food sources effectively dwindled or vanished.
Leaving them high and dry, ironically.
Exactly. This led to their rapid decline and eventual extinction, and consequently, the carnivores of the time, those dominant crutarsans,
Their prey disappeared.
suddenly found their main prey, the once abundant Rhynchosaurs and Dicynodonts, disappearing. They too would have lost a significant portion of their food supply and followed their prey into decline.
It's a whole ecosystem unraveled for them.
So it's not necessarily that dinosaurs were somehow inherently better adapted in a direct physiological sense to the wet environment itself.
Not necessarily faster or stronger because of the rain.
But rather, they were just the only major group of reptiles left standing, or perhaps more accurately, the only major group of land vertebrates that could effectively utilize the new dominant food source.
Right place, right time, right digestion.
This biological niche, left wide open, allowed them to flourish and completely take over, setting the stage for their 150 million year reign.
Exactly. The precise mechanisms of why the rain helped the dinosaurs might still be debated among paleontologists. Was it direct competitive advantage, a sort of survival of the fittest in a new environment, or simply being the last ones able to eat what was available?
The details are complex.
But what is undeniable is the profound correlation. Dinosaurs became dramatically more abundant during the Carnian Pluvial episode, and just as profoundly, the Dicynodonts, the Rhynchosaurs, and many of those early crutarsans that had dominated for so long very quickly went extinct or dramatically declined during the same period.
A complete turnover.
A changing of the guard in the terrestrial ecosystems, driven by fundamental shifts in the climate and consequently the food web. It highlights how tightly coupled Earth's geological processes are with the very evolution of life.
This raises an important question, doesn't it? What on earth caused it to rain for 2 million years in the first place?
The ultimate trigger.
I mean, that's an extraordinary climatic anomaly, far beyond anything we typically observe.
It really is.
Well, the scientific consensus points to a huge burst of volcanic activity that occurred just before the rains came, around 235 million years ago.
Volcanoes again.
Indeed. This wasn't some minor local eruption. This was a truly colossal event, forming what geologists call a large igneous province, or LIP.
LAP.
This particular LIP, known to geologists as the Wrangelian eruptions, was primarily located in what is now Alaska and British Columbia.
Rangelia.
And when I say colossal, I mean truly gargantuan. These eruptions lasted for more than 5 million years.
5 million years of eruption.
Ceaselessly churning out an immense volume of lava that eventually reached an astonishing 6 kilometers thick, covering an area of perhaps 250,000 square kilometers.
Just the unimaginable scale.
Think about the sheer volume of material being ejected, the continuous outpouring of molten rock from Earth's interior.
And crucially, these eruptions weren't just spewing lava. They were releasing an immense sustained amount of carbon dioxide,
The greenhouse gas.
a potent greenhouse gas, into the atmosphere. Estimates suggest enough CO2 was released to raise global temperatures by about 3 to 10 degrees Celsius worldwide over that prolonged period.
3 to 10 degrees warmer globally. That's huge.
It's a massive shift. Now, over a very long period, warmer temperatures, counterintuitively perhaps to our immediate perception of climate change, can actually create a much wetter climate on a global scale.
Warmer means wetter. How
Because higher temperatures accelerate the Earth's water cycle. More heat means more energy for evaporation surface water from oceans, lakes, rivers into the atmosphere, leading to more moisture in the air globally and therefore more precipitation.
Okay. More evaporation, more rain.
It's a supercharged hydrological cycle, a more energetic atmosphere capable of holding and moving far more water. And in fact, because of this significant increase in atmospheric moisture, the Carnian Pluvial episode is sometimes also referred to, perhaps more accurately, as the Carnian Humid episode.
Humid episode. Makes sense.
But, the Wet Intermezzo does still have a certain ring to it, doesn't it?
It does.
Anyway, after about 1 million years of this intense volcanic activity pumping out greenhouse gases, the atmosphere became so warm and so saturated with moisture that rain could finally reach even Pangea's vast, previously arid interior,
Penetrating that dry heartland.
leading to those sustained global deluges.
So the obvious follow-up question is, how did it stop? If volcanoes kicked it off, what eventually turned off the tap after 2 million years of continuous rainfall? That's almost as remarkable as the deluge itself.
It is, and what's fascinating about our planet is its inherent ability to self-regulate, especially concerning carbon levels and long-term climate.
Earth sorts itself out eventually.
Kind of, yeah. When carbon levels in the atmosphere become incredibly high and stay there for a very long time, Earth has natural, built-in mechanisms that work, albeit slowly, to reabsorb that excess carbon and get it back into the ground or ocean where it belongs. It's a slow, powerful planetary-scale carbon sink, acting as a geological thermostat.
How does that work? What are the mechanisms?
There are a few key processes at play here, all working in concert over immense timescales. Firstly, plants are fantastic at this.
Right. Photosynthesis.
They take in vast amounts of atmospheric carbon dioxide through photosynthesis and store it in their tissues. With the newly wet conditions, plant growth, particularly of those large conifers and Bennettitales we discussed, would have exploded,
Sucking up CO2.
drawing down significant amounts of CO2. Secondly, the slow, relentless process of weathering and eroding rocks also absorbs carbon from the atmosphere.
Rocks absorb CO2.
Chemical reactions involving rainwater and rock surfaces draw CO2 down from the atmosphere, ultimately leading to its incorporation into minerals. It's a slow chemical process.
Fascinating.
And thirdly, and perhaps most significantly on a long time scale, the oceans soak up vast amounts of CO2 from the atmosphere.
The ocean carbon sink?
Exactly. This dissolved CO2 then combines with calcium and other minerals, often with the help of marine organisms, to form carbonate rocks like limestone. These carbonate rocks precipitate out of the water and accumulate on the seafloor, effectively locking the carbon away for geological eons, sequestering it out of the active carbon cycle.
So multiple natural processes slowly pulling the CO2 back down.
Precisely. So, as the Wrangelian eruptions eventually slowed down and finally ceased, the Earth's natural carbon cycle was gradually able to stabilize. The excess CO2 that had built up was slowly but surely reabsorbed from the atmosphere through these various mechanisms.
And the climate cooled, the rain stopped.
Consequently, the atmospheric greenhouse effect waned. The supercharged hydrological cycle slowed down, and the Carnian Pluvial episode gradually came to an end. By the time the eruptions had completely ended, around 230 million years ago, the world had, remarkably, returned to a classically hot, dry, Triassic climate,
Back to normal Triassic conditions.
a condition that persisted for millions more years until the supercontinent Pangea itself began its monumental process of breaking up, leading to further climate shifts down the line.
And what a journey it was. Because even though the Carnian Pluvial episode was, in geological terms, relatively short, only 2 million years out of Earth's 4.5 billion year history,
A blink of an eye, geologically speaking.
its impacts on life were absolutely permanent, profoundly reshaping the trajectory of evolution on Earth. All that rainfall, that incredibly long wet intermezzo, helped conifers, those resilient cone-bearing trees, to spread and diversify dramatically across the globe.
Gave them a real boost.
This period was crucial in the evolutionary lineage that led directly to the pine trees, firs, spruces, and other conifers we know and recognize today. So, next time you see a pine tree or enjoy a coniferous forest, spare a thought for those 2 million years of relentless rain that helped them establish their dominance.
A wet start for the pines.
But the truly transformative legacy, the one that truly altered the course of life on Earth, was the dramatic shift it brought about in the animal kingdom.
The rise of the dinosaurs.
The start of the Triassic may have been the land of weird croc-like things running on their hind legs, and those bill-and-tusked Dicynodonts, creatures well suited to the arid plains. But by the time those 2 million years of rain had ended, the world had fundamentally changed. It had fully, irrevocably entered the age of dinosaurs.
Like a complete regime change.
The climate, the geology, the very availability of food, all orchestrated by volcanic fury and a supercharged water cycle, had inadvertently but decisively created the perfect conditions for dinosaurs to dominate, driving many of their previously successful competitors through a process of environmental filtering and competitive exclusion to extinction. It's an astounding story of planetary dynamics dictating the rise and fall of life, demonstrating that seemingly subtle shifts can have colossal, long-lasting evolutionary consequences.
It really underscored the interconnectedness of it all.
So what does this all mean for us? Well, we've taken a deep dive into an incredible chapter of Earth's history, from the extreme arid conditions of the early Triassic through the unexpected and absolutely astounding 2 million year rain event, the Carnian Pluvial episode that followed.
Quite the story.
We've seen how this profound climatic shift reshaped global ecosystems by favoring new, tough plant types, and how this inadvertently created the perfect environment for dinosaurs, with their particular digestive advantages, to rise to undisputed dominance, driving many of their previously successful competitors to extinction. It's a powerful reminder that stability is often an illusion in geological time, and that adaptation is a continuous, sometimes ruthless game.
Absolutely. And if we connect this to the bigger picture, this story of the Carnian Pluvial episode offers a powerful reflection on the sheer scale of geological time and the profound, sometimes slow, sometimes sudden, ways in which seemingly stable ecosystems can be dramatically and irreversibly altered by long-term, large-scale climate shifts, especially those driven by deep geological forces like massive volcanic eruptions.
Makes you think.
It makes us ponder what similar, perhaps slow-burn shifts might be occurring today, driven by different factors, of course, and how those changes might subtly or not so subtly shape the world for future generations, and indeed for the life forms that will dominate it long after us.
A sobering thought, perhaps.
It's a testament to the Earth's dynamic nature, constantly evolving, constantly reshaping life.
Absolutely. It certainly gives you pause for thought, doesn't it? Thank you so much for joining us on this truly fascinating deep dive into Earth's ancient, wet past.
A pleasure.
If you've enjoyed this deep dive, please do like, share, and subscribe to our channel. And we'd absolutely love to hear your thoughts and questions, so do put them forward in the comment section below. We really do read them.